for joining us. We're here to talk about BC pipelines. We want to talk about Saskatchewan pipelines, But we have our AI and machine learning team right here. So we have Mann and Godman here, and they're here to talk about BC pipelines. Now, obviously, that's been a big issue that hasn't been regulated, doesn't really make that available for a lot of pipelines for BC. It's kind of been a gap for a lot of years. Things analysis. So it's probably the best BC pipeline routing data from any other sources, and it's quite complete. So with further ado, I'm going to hand it over to Matt to talk about the practice of the project and how we solve that, how we track that.
Hello everyone. My name is Matthew. I'm one of the machine learning engineers here at AbaData. I've been here for about a year and a half, and yeah, I'm super excited. BC Pipelines is a big project that we've been working on for quite some time, and I'm excited to present this to you guys as a full finished project. It's awesome. We're still doing some of the implementation, so when I say finished, it's like here there, but you guys are going to be able to use this as of today. Like it's ready to go. BC Pipelines bridging the gap. So raise your hands if you've ever heard of a pipeline. Fantastic. You're in the right place. Raise your hand if you've ever heard of BC. Perfect. You guys fit all the requirements to understand BC Pipelines. So here's how we're gonna do these things today. We're gonna start with an introduction. Congratulations, we're already at that part. Now there's only a couple more parts to get through. So next up is my favorite part, the data and machine learning approach. After that, Quinn's gonna talk to us about validation and rectification. After that, we're gonna do integration and a demo as long as the Wi-Fi is working. And finally, we're gonna take some questions, and I hope you guys have plenty of questions for us about the BC pipelines. So let's talk about the problem. The problem is that there's not really any good data sets for public pipeline paths. So there are about 22,000 pipelines in BC that are in the ground buried and have had oil or gas or whatever flowing through it. The public pipeline path data only accounts for about 5.6 thousand of these BC pipelines. And many of these missing pipelines and the pipelines that are not publicly available are historical pipelines. So pipelines that were built before 2016. So our goal is to utilize any available resources to infer the locations of all of those pipeline paths. So we want to try to get about 16 or 17,000 pipeline paths, and we want to figure out how to do that. So let's move on to my favorite part, which is the data and the machine learning approach. I love machine learning, so it's my favorite part. Let's start with the question, how do you find a pipeline? Here we see some satellite imagery, and you might be able to infer yourself where some pipelines might be within this image. On the left, we see just the normal RGB, the image of the satellite imagery, and on the right, we have something called the normalized difference in vegetation index. What that is meant to give you is the approximate vegetation in any pixel within the satellite image. And you can say, like, this might actually work. This might give us some data as to where the pipelines are within BC, because you can kind of see that it's a little bit darker here and here, and over here where there's like lots of trees and stuff where things wouldn't be run through, then it's a bit brighter. And so you can say, low values are where pipelines might be viable, and higher values might be where pipelines are not viable. Another method you might use is, this is a satellite image from 2016. This is right before a pipeline was built. And here's from 2017. So this is right after the pipeline was built. And you might see that in this farmland, you have found where the pipeline is, because there's this huge scarring in the earth where the pipeline has been dug and installed. But there's a couple problems with these approaches. These approaches would be nice if they worked really, really well, but we have a couple problems. The first problem is that NDVI, or normalized difference in vegetation index, is really noisy. So this image here, this is the NDVI of this satellite image. Now, if you're trying to find a pipeline path, it's going to be a lot more difficult when your NDVI graphs look a little bit like that as opposed to the other really nice one before. Another problem with the second method I showed was that pipelines are old. Most pipelines weren't built in 2016, and most of the pipelines that we need to find the paths for were built long before 2016, 1980, 1990, those sorts of things. And finally, we don't have an end-to-end algorithm with any of these things. And so what we really want is to make an end-to-end algorithm in order to find our pipelines. So let's talk about what we do have and use that as a starting point. So we have already the paths for about 5,000 pipelines. I think it's about 5,600. And we have the project details for about 22,000 pipelines. The project details includes things like the status of the pipeline, when it was built. I think I already said status, but it starts at its starting location and its end location, which are either NTS grid squares or LSD grid squares. We also have the approximate length, the listed length, and other different things that you might already find inside AbaData as well. In addition to that, we obviously have AbaData's data sets. Now, AbaData has countless data sets that we could probably use to our advantage in this project. And we have 6-band satellite imagery. So the Sentinel-2 satellite has lots of imagery for us to use. So how can we leverage this existing data? Well, particularly we can leverage 3 types of data that we have already. First is the wells. So the wells are going to give us an indication, since we just have the grid squares and we have exact well locations. These exact well locations might give us an indication to where a pipeline might start or end. River, because obviously you don't want your pipelines running through rivers. We're going to be able to use that to help us indicate where the pipelines are not going to be. And finally, we're going to use parcels and right-of-ways. Our parcels and right-of-ways are going to also give us an indication of where pipelines have been intended to be built, except that we don't know that these right-of-ways are specifically pipelines all the time, but we do know that they exist, so they can help us out along the way. So the next approach that we used was we have all of these right-of-ways, these parcels that are labeled as statutory right-of-ways. And there's all these big, thin lines, thin as in 30 meters, but thin lines that span across the province. So what we can do is we can build out a giant grid, a giant spider web essentially of right-of-ways, and then we take the pipelines at where they start, we choose a point in there, we choose a point in where they end, and then we take the shortest path along that graph. But unfortunately, one of our early insights was that these right-of-way files have holes in them, the statutory right-of-way parcels have holes in them where there might be certain buildings or there might be certain other things. And these holes are obviously going to cause us huge problems, because if it can't find a way by going just directly to it, it's going to find another way. And the other way might be 100 kilometers in a giant loop that goes way off, and obviously this is not where our actual pipeline is. So that was one of the early insights that we had. So let's take a moment to talk about viability scoring. So one of the really good advantages of the NDVI was that it was going to give us some sort of indication of where a pipeline might be viably built and where it might not be viably built. For example, it might not be viable in really forested areas without tree line cuts and those sorts of things, but it might really be viable in places that do have tree line cuts or coming out of a bad site and those sorts of things. What we want is some sort of an index that gives us directly a pipeline viability score. And since I'm a machine learning engineer, I decided to employ a little bit of machine learning in order to do this. This was a 4-step kind of program, and you'll see that it's a cycle actually. But the first step is to annotate data. I downloaded 50 satellite images from around BC, and I painstakingly marked every single pixel as either being viable or not viable. And so from that, we get 50 full images of viability or not viability with their labels. The second thing we can do is design a neural network. For this, I employed advanced techniques such as UNets, dice loss, cross entropy, different things like that. The technical term is called semantic segmentation. You can use skip things. I do have a quiz on this afterwards, so I hope that you're all right. After you design your neural network, you want to train your neural network, and this is a really important thing, is that your neural network can actually memorize every single image that you put in there, and will just give you the outputs that it's memorized. And so one really important thing that you have to do is you have to take about 10% of your data and set it aside into what's called a validation set, so that you can validate that it's going to continue to work on satellite images that it's never seen before. That way we can use this on all of the satellite imagery over all of BC. Finally, we can infer. We now have a model that we can give satellite imagery and it will output pipeline viability. But the bonus to this is that if it can give you pipeline viability, it can annotate new data. And so this makes the annotation process really, really quick, because then all you have to do is let it annotate the data and then the human just corrects it. So after this, I looped it around and around and around, and I went from 50 images to about 250 images in about the same time as I got the first 50 images, which was really sweet. So then that led to a really nice inference model that could test out, that could output pipeline viability. It's not perfect, but it's a lot closer than NDVI is. And here's the results of that. So here's the satellite image that we got. Here's the NDVI score. Obviously, there's really not much that you can do with that. Here is the pipeline viability score. So obviously, if you have something like that starts here and it ends here, then you can kind of find a path that goes along this pipeline viability score. It's a little noisy, but it will work for what we want it to do. Here's another example of, on the left, is NDVI score. Obviously, there's hardly anything intelligible about that. This seems like the kind of thing a psychologist might show me and ask if I see anything. But when I look at this one, I see pipeline viability. So another one of our early insights, and this was a kind of a funny one, is that because of the lack of vegetation and the sort of thinness of riverbeds, the model really thought that riverbeds were pipeline viable. And as you guys probably know, we don't want to be building a pipeline that just goes right along a river. That could lead to millions of dollars of liability, and obviously it's just not where we're building pipelines. So let's talk about how we utilize this pipeline viability scoring to actually get the paths as output. First, we wanted to align the endpoints. As I said before, we had the well data, and the wells, if you have a well within your grid square, then it's a very high likelihood that your pipeline, the endpoint or the start points, are going to be at that well, whether it's just connecting at that well to another pipeline segment, or it's just coming from that well to a facility. For other pipelines, it's a reasonable likelihood, if you have that within the grid square, that these are intersecting pipelines. And actually, we did this one pipeline at a time in chronological order of the way that they were constructed. So it's reasonably likely that the pipeline that got constructed then fed into the existing pipeline that was already there. And finally, if we don't have any of those things, then we use the pipeline viability density. So if we go back to this slide, you can see that there's a pad site, and that pad site is really pipeline viable, and it's really dense. Like, there's a lot of pipeline viability in that area. So then we decided that that is a good indication that there's either a pad site or a well or a facility there, and we took the most pipeline viably dense area and we set that as the endpoint. So that's our method for finding the endpoints of all of the BC pipelines. Now that we have a precise end and a precise start, we can find a path between the start and the end. So a couple intuitions here that we use for the algorithm. First, we want to find the best path, the shortest path. Builders obviously don't want to be using a ton more resources than they have to. So they're not going to purposely make a longer pipeline than they need to. The second one is pipeline viability. Obviously, we want to do places that look like they have a pipeline in, as opposed to places that don't look like they have a pipeline in. Next is the right-of-ways. If these are available, they're not always available, but if these are available in the area that the pipeline is, then of course we want to use these, and we'll mark right-of-ways in area pipeline viable. And lastly, we have the river data, and we want to avoid crossing these any more than necessary. So here's an example of using the endpoint alignment and pathfinding. On the left, it's really hard to see, but you can see that there's paths that are going down here from pad site to pad site, and it's finding the paths between these, and these are actual pipelines from the regulator that we've been given to the start and endpoints. Imprecise, and so we've actually found I believe that there was actually wells for each one of these that we lined up the endpoints for. So in red is our pipeline viability, in yellow or green, that's where the right-of-ways are, and in blue, that's where all of the rivers and water bodies are. And so we would use that to score each pixel between 0 and 10, and we would find the lowest cost score to get from start to end for each of the pipelines. So here's a graphic that shows the current data that's available publicly for pipeline taps, and here is our generated data set. And it fills it up almost completely. I mean, wherever there's pipelines, there's pipelines now, so it's pretty sweet. So in AbaData's data set, we want to just make a direct comparison to where we started from and where we've gotten to. We have 22,000 total segments, as opposed to the public data set, which has 5,500 in total segments. We have 12,000 active segments as opposed to the original around 4,000 active segments, and these are active pipelines, that is. And here's a really important one too. If you have suspended or inactive pipelines, the old public data only had about 1,500 of these for the segments, and now we have about 10,000. So that's going to be really important if you're trying to dig around one of these old pipelines. Well, before it was going to be very difficult to find out where that was, and now it's going to be much easier. So I'm going to hand it over to Quinn now, and he's going to talk about validation and rectification.
Hi everybody, my name is Quinn, and I'm a GIS analyst at AbaData. Today I'm going to be talking about some of the validation and rectification methods used by myself and my team to ensure the accuracy of this data set. And then I'll go over a few ways you can leverage AbaData's current tools to analyze this feature. Now, luckily for me in my career, the machine learning processes used to generate this data aren't perfect yet. These models are great at creating the initial network, but they still make mistakes from time to time, and that's a good thing actually. These imperfections give us an opportunity to turn what the model initially generates into something that is usable in the real world. And just to clarify, when I talk about validation and rectification, what I really mean is taking what the model gives us, so its predictions, and checking if this solution matches reality. Okay. The dataset Matt generated was a great starting point, so it does a huge majority of the heavy lifting, generate thousands of kilometers of pipeline alignments, something that would have taken months and months to manually digitize. But our goal for this project wasn't just to get a broad view of where pipelines might exist. We wanted to create a data set that was spatially precise and that represented the actual location of assets on the ground. To reach this level of accuracy, every segment produced by the algorithm goes through a full human review process, something that helps us shrink the gap between prediction and truth. Sorry. Okay. This is kind of like a broad overview of my workspace during this whole process. Each line you can see here represents a generated pipeline segment that has been validated or is going to be validated eventually. To help us determine whether these geometries are accurate, we've used a combination of spatial analysis tools as well as a few verified data sets. Again, things like right-of-way boundaries, facility model site locations, and satellite imagery. All of this data works together to help us determine where these pipelines actually are on the ground. And beyond these tools, we've also employed a pretty simple but effective human confidence rating. Sorry. Let's do this.
Yes, one second. Well, is it other do appearance?
Okay, sorry. These ratings tell us how confident we are that a segment accurately reflects the location of an asset. So all of them we have, again, a high, medium, or low confidence rating. And these ratings are based on several key factors. So things like the accuracy at the start and end points, how well the line is aligned to its corresponding right-of-way boundary, Whether it's like a continuous fluid line from asset to asset, or if it's broken into fragmented segments. The connections of the target pipeline to other assets in the area, and if these connections actually make sense. And whether the segment is drawn on or around visible terrain features like tree clearings or landscapes. A high confidence segment would satisfy all these requirements easily, but it would be clean, continuous, and consistent with all of our verified data sources. A low confidence segment, on the other hand, would be completely disconnected from networking, found outside of any environmental indicators, or not aligned to any of the right-of-way paths. This rating system has made it much easier to track progress throughout the review process and gives us an indication of the areas that might need a closer look in the future.
Super. Go.
Here's a pretty good example of a strong prediction. On the left image in the white are the target well sites. In the middle, the blue line is the right-of-way between the wells that next to them, and the red line here is the actual generated predicted pipeline path. Everything in this example lines up perfectly with all of our reference data sources. Again, the alignment follows the right-of-way. The points are spatially accurate, the endpoints, so they both terminate within the well sites properly. And the line matches any visible star in the left image there. It's consistent, it's logical, and again, it satisfies all of our requirements, so we get a high confidence rating immediately from any of this. On the other side though, this is a pretty good example of a weak prediction here. In this example, the model generated a line that's kind of roughly in the right area between the two sites, but there are still a few glaring issues here. The line segment starting from well site A terminates in some sort of water body. It's kind of hard to see like it does, and it also doesn't connect to the next pipe in the sequence properly. The next pipe also has inaccurate termination points. It stops kind of way down the service road, way past its target site B. The length of these segments,
It's brutal.
the length of these segments also do not match up with any of the regulator data that we have. And on top of this, again, none of these segments follow any of the environmental scarring that you can see on the image here. This kind of mistake that you can see is actually one of the more common error types that we run into when reviewing this data. The model technically did what it was supposed to, but it just wasn't the right choice here. It found a point from point A to point B where it wasn't right. Again, all of these factors kind of make it pretty clear that this is a low confidence prediction. But here is actually an example of how we would rectify this. So in this case, we don't have any help from the right-of-way path data. The closest right-of-way path would be over a kilometer away in all directions. So what kind of measures would actually still be useful in rectifying this? Here, the main important ones would be the termination points of the lines. So again, well site A and B. We want to rectify it to make sure that they end in those spots. The length of the segments themselves as well. So previously, the first connection point was around 500 meters. It should be closer to 450. And the second one was over 1,400 meters, and now it's rectified to be around 750, which is way more accurate. And then on top of that, again, we would use satellite imagery. So it's, again, pretty difficult to see. When I was doing this, I would be looking way closer at these images here. But there is sort of a path from that water body all the way to the well site B. This is a great example of the difference between what a model predicts and what a human can actually infer from context clues and the environment. Again, the algorithm did exactly what it was designed to do. It just didn't have enough information to make the right prediction here. Now, that being said, not all of the model's predictions were this far off, and in fact, most of them weren't at all. I personally reviewed a huge number of the generated lines since I started on this project, and a vast majority of them have been given a medium or high confidence rating. The point of showing this weaker example isn't to highlight the failures of the model in any way. It's more to show what our validation process looks like, the methods we use beyond machine learning to improve the accuracy of the network, and how we've used these imperfections to help refine the process overall. We're not just polishing the generated data and saying that that's good enough. we're working to build a robust, comprehensive representation of BC's pipelines. One that sets the standard moving forward and provides a framework for future projects across Canada and internationally. So after all this review and refinement, what can you actually do with this data? One of the biggest advantages of bringing the BC Pipelines data set into AbaData is that it's fully compatible with the same workflows you currently use in Alberta and Saskatchewan. You can filter these new pipelines by their attributes, buffer them to a huge variety of features on the site, and run spatial queries to find crossings or missing links in the network. The measurement and analysis tools you use daily, so things like distance measures, elevation profiles, and link calculations also will work seamlessly with BC. And even tools like risk assessment and pipeline integrity will work exactly how you're used to. Again, nothing about your process has to change here. Same everyday routines that already work for you in Alberta and Saskatchewan now extend into BC, giving you one continuous, comprehensive, cross-provincial map. To demonstrate this, Matt's going to give you a quick walkthrough of the ASF's capabilities on AbaData.
I'm back. Cool. We're gonna log into AbaData. Yes, you guys can see that. Okay, perfect. It was 2 screens before, so I'm glad that it's 1 screen now. All right, don't tell anyone my password. Cool. So you might not believe this, but we're actually, this is supposed to be loaded by now. You might not believe this, we're actually already in BC. This is the BC Pipes data set as it stands in AbaData right now. This is under pipelines. It's under BC Pipelines trial. We also get all of our other favorite AbaData features that we get in Alberta and Saskatchewan, such as your flow direction. As you can see, you can also do company filtering. So let's say I want to just see Tourmaline's data sets, or Tourmaline's pipelines. And we can get that there. You can open up each pipeline. You'll get all of your favorite data that you guys love using, such as construction dates from locations to locations, your products, your length, all of those sorts of things, H2S status. All of the things you love most in AbaData are in here. You can also get the elevation profile, as well as if you have access to the triage products for pipeline integrity, then you can also get the engineering assessment for your BC pipelines as well, including internal risk, external corrosion risk, mitigation, and hill slope analysis. You can also do attachments, comments, all of your favorite things that you do inside of AbaData right now in Alberta and Saskatchewan, you can do inside AbaData for BC as well. You can generate reports that include BC pipelines here, and include most of the same filters that you would be able to use elsewhere. So that's AbaData BC pipelines. That's what we got, and give it that 5 here. And if you guys have any questions for us, we would love to hear them.
Obviously, this is a really big project for us, many hours, and there's a lot of variables went into it too. One of the things that Matt didn't mention is we have satellite imagery going back to the early 80s, and so we're able to take a look at around the time the pipeline was constructed, before and after, if there's a tree cut line or it's starting with new farmer scale, we have data going back to the early 80s. And so you might ask, the next question you might ask about that is, why is that not available now that the historical satellite imagery? And that's one of the things that we're working on, is we're working on getting historical imagery back to the 80s. Hopefully in 2026 we have that. No real firm update on that just yet. But yeah, we'll roll into questions, but great work from Matt and Quinn. Thank you.
Yeah, that's awesome. Good work on that data set. Compared this to your better to India or to monitor to there's just a guessing game. Hey, not all the pipeline here. They're wrong. Yeah. Request active fluency data as a tab on there.
You'll just say,
going pipeline or the caves up there, it's legal stuff.
Yeah.
And use priests set up.
That's a good suggestion.
Yeah.
For sure. Thank you. Just so people in the room can hear, if somebody has a question, we'll get Andy to hand to the mic and we'll just.
I told them not.
Yeah, right there, yeah.
I just want to say this is really cool, and Matt, I could talk to you all day, but I'm really curious if wood lots or wood cuttings of any kind, when you were building this out and doing the machine learning process, if that created any conflicts in the data that you're receiving back because they look so much like well pads. And then furthermore, are you using this data or this tool for any kind of pipeline siting work? Or has anyone mentioned that to you? Because it seems to me that this is.
That's really good pipeline construction, you're saying?
Well, pre-siting, routing.
Yeah.
Before pre-construction, like what's my most viable route between point A and point B using somewhat of the same method than that kind of
Yeah,
thing?
I'll take the first part of the question and then that we try the later part of the question, I'll take the first part. So certainly, that is something that we've thought about is routing for pipelines. We have elevation profiles. I don't think Matt showed that in this one here, but even for BC pipes, we have elevation profiles, which is obviously a key feature. Which going across streams, we obviously want to cross water bodies more than we have to. But certainly elevation and terrain. It's something that we thought about. We haven't actually actively done anything with that just yet, but it's certainly a great idea. The first part of the
Yeah, that's a great question. And just like in the pipeline viability, it probably did end up having some sort of an impact where it would look like it was a pipeline viable area. Thank you. Where it would look like a pipeline viable area. But the thing is that we don't use every single pipeline viable area. It would just be if there was like a well in that, or like if there was a pipeline that wanted to move through it. But the advantage of, like wood yards and those sorts of things would be the fact that it would probably cut off at some point. So the pipeline going through there that wants to go to a further on location would not want to use that path because it would then have to go through somewhere not pipeline viable.
But I just thought of one thing I'd like to add about this too, and to bring the mic up here if you want. Any question over here, but it's also one. So we've actually made some pretty big investments in the development team, and so we mentioned something Ninja. I don't remember what it was called, but so we have probably the largest, probably by a factor of 3 or 4 candidates, and somebody like Patrick Angel. And so we're reinvesting in the company, bringing new capabilities into AbaData, leveraging AI, machine learning, and so we're looking to do some really cool things over the coming years. And but we love it. We hire people that love doing what they're doing. These guys are awesome, and yeah, we're going to do some really cool things in the coming future. So I think there's a question there.
Yes, sir. I'm not sure if it's related exactly to this topic, but I have a challenge sometimes working connectivity when I'm trying to connect, let's say, pipeline to horizontal wells. So first question is, if you have faced that problem, say for instance that a horizontal wells with same sort of location but different downhole locations. What I've done is basically to do manual data analysis to see which to differentiate by substance and downhole locations, because those connectivity are very challenging sometimes because it's hard. So yeah, I'm not sure if it's really.
So we actually have a whole connectivity module that we developed out. I think we may have talked about that in the pipeline integrity session today. I wasn't in that. But we actually have a whole connectivity module. So as far as like downhole and surface locations, so we have most of those locations. So with our connectivity module, we've taken into account a whole, probably 50 different factors. Obviously, licensee was at the time, construction substance, the diameter of the pipeline, material, there's a multitude of factors. So we have an automated connectivity algorithm that we have discussed here. It works with BC pipes as well. So it's a pretty awesome. I don't know, have you seen it? Our connectivity tool?
Yes.
Okay.
But no.
Sorry to the odds.
Yeah.
Okay. But yeah, I mean, if anyone wants to see that, we can set up the demo for that at a meeting. and show you exactly how it works. So it's, with any connectivity tool, you can kind of get 90-95% of the way, but it's kind of that last little 5 or 10% that is a little hard. We have some really great tools for manually finishing off that last 5 or 10% to give you all those different information that comes along with the pipelines.
Kind of a two-parter. Is there anything to distinguish the lines that have been kind of drawn in to fill in the blanks through this method, which seems like it's going to be extremely reliable, but is there anything to flag that, this is a theoretical position as opposed to, one that we absolutely know because, it was put in the ground and we saw it happen? And then the second part is is there any avenue for industry, once they pad locates to verify a line or daylight and that kind of thing, that they can confirm back to you guys, yeah, this one's real good, check it off the list, or this actually wasn't where it was shown on here, can we correct it, that kind of thing.
Well, I'll take the first stab of that, and if you have anything to add, then you can. So in our database, we know which ones drawn in by machine learning and came in the loop. And it's just a flag in the database. And so we can easily turn around, because there is regulated data since 2016, I believe it was. That's kind of more official data sources. And there are no good official data sources prior to that. We currently have, because if you turn the pipelines layer on, I think it shows the layers from the pipes from 2016 on. We actually have it separated in the interface into DC pipes. At some point, we'll probably merge those together, I think. But it's a good idea is to have a flag in there, just some way of identifying it. If it's done through machine learning. I don't think it's going to be 100% perfect, but it's going to be better than anything that's out there. But there is potential for some mistakes to look at. So that's a good suggestion.
What is the official data source of these pipelines to validation?
What was the question?
What is the official data source of the 52 or 53 modern pipelines that you actually saw?
Yeah, absolutely. We get those, the 5655. We get those from the BC Energy Regulator, which is the BC data. Yeah.
Yeah, question back there.
I have a few questions. One kind of tied to his question there. Is there any plans to do any kind of physical field locates for the pipelines?
It would cost a lot of money for us to go out and do those surveying to that. So I think from AbaData standpoint, the answer is probably not. We have looked at doing wide-scale LiDAR scanning of entire provinces. Something we're looking at that will give us additional information, like ground, because of the ground scarring or different ground shapes and stuff like that. But actually, boots on the ground, unlikely. Now, if that data comes in from our customers, we'd love to bring that in and make the data more validated. As far as having it ourselves, unlikely.
The second question is, with the ones that are a little bit more theoretical, how do you determine the ownership of those theoretical activities?
The ownership of those pipelines would be actually from the project details, and so that's where we're getting like licensing, operating, and stuff like that.
And then my final question, is there any plan to expand this further east?
Yeah, to like Ontario or Eastern Canada. Yes, yeah, I think so. And we talked about doing this kind of thing worldwide too. But it's a bite only what you can chew, I guess. It's one step at a time. So we do have intentions to expand out from Western Canada where we are right now. So one more question.
Hi there, it's just a real quick question. How often one get out? I know Alberta's like 2 months, 1. What are you guys looking at with BC?
Yeah, absolutely. I think our plan is to integrate it just like we're integrating all of the other regulatory data. So we have monthly updates, and I believe I don't know the exact interval of updates that they send out, but we'll be taking up their updates as they come out.
Okay, well, I think that's all we have for time. We're going to be over at the main hall there. We're going to talk about that roadmap. But thanks for everyone coming.